computer. Okay, so I will be recording on my laptop, and hopefully I can get it uploaded to you all. If not, there will be an annotated version of the notes that I will be sending out for sure to everyone. That includes the PowerPoint and then just some of the examples that we will all be going through. And then Kristen, do you mind sharing your screen first, since you're starting out the PowerPoint?
Sure, I don't mind. It's so buggy, I think, because I have so many tabs open. Sorry. All right, so slideshow. Okay, yeah, so let's just get started with part one, which is structure, bonding, and molecular properties. We've covered these sections as listed. We'll have all of the corresponding sections below. So diving right into atomic orbitals, this is basically a hypothetical cloud where your electrons can be. So we have one listed for s orbitals and p orbitals. The node, technically with atomic orbitals, there's like nodes and antinodes, and we'll see that later on with molecular bonding. But right here, our node is basically just to represent the nucleus. So as we know, the s orbital is in the shape of a sphere, and p orbital is kind of like a dumbbell. There's no d orbital, so I don't think Tovar covered that too in depth, but the p orbital exists in 3 dimensions, or sorry, they all do, but there's 3 planes for p orbitals, so px, py, and pz. And the number of orbitals there exists for each letter increases as you go from S to P to D. So it goes 1, 3, d orbitals have 5, F has 7. So next, let's go to chemical bonding. A lot of this is reviewed from Gen Chem, or even if you saw this in high school. So we have our basic ionic bonds, which is the actual transfer of electrons. Like one atom is giving its electron to another. And that's usually seen with ionic interactions like salts. So NaCl, Na is donating its 1 valence electron to complete chlorine's octet. So that's the whole goal of bonding, is 2 atoms want to achieve a level of stability that's given when you have a full octet. It's kind of different with covalent bonds because they're sharing electrons equally. And again, it's done so that atoms can complete their valence shell. So for example, like carbon dioxide, each C and each O is sharing their electrons. And they can be either polar or non-polar depending on the electronegativity of each atom. And one note on this, if you go into problem set 2, if you're in pilot, problem set 2, number 4 basically describes this. And there's a differentiation between partial bonds and dipole moments. So if you're a polar molecule, you are a dipole, like 2 poles, because there's unequal sharing of electrons. In number 6, we asked you to label partial charges. And this is different because it's just showing a disproportionate electron density, and that's seen through resonance. So one note I would keep in mind is dipole moments cause partial charges, but you shouldn't use these terms interchangeably. Next, with valence bond theory, this is kind of everything you learned with bonding up until orgo. So don't think about molecular orbitals. This is what you think should happen with a bond. Like 2 atoms come together and they form a bond. So I've shown that with 1s, like 2 hydrogens. There are basically 2 big theories in quantum mechanics we use to describe bonding. So one is what we're doing now, valence bond theory, and the other one we'll go into later, which is MO theory. So what is valence bond theory? It's the assumption that bonds are localized and formed by each atom donating an electron to form a cloud. So each atom is contributing an electron. It should be noted, this is largely invalid because we've seen through resonance and lone pairs that atoms can bond with delocalized electrons. So right now, valence bond theory, just think of the electrons as like hammered down or something. They're not exactly resonating, but it's each atom contributing one. So the TLDR, it's kind of like covalent bonds between two atoms, right? Because covalent bonding is sharing electrons. For molecular orbital theory, this is actually based on resulting two atomic orbitals, and that comes from the principle of conservation of energy and mass. So if you throw in two atomic orbitals, there has to be like the sum of that has to equal the sum of molecular orbitals. So we see here you have, again, two H's. Those are your two atomic orbitals, and they form two molecular orbitals. We don't really see the anti-bonding, which is sigma star up top, but it's there to kind of as a way to rationalize and our theory for saying energy is conserved. So the number, it's conserved. The bonding orbital is filled and forms a stable bond. And since the anti-bonding orbital is such high energy, it's, how do you say it? It's basically just think of it as way higher energy and way more unstable. So it has a node in the middle. And here's an example with nitrogen. So nitrogen has three, like a triple bond. 2, 4, 6. Why are there 3 dots? That should be, is it not like one lone pair? Anyway, so when looking at the molecular orbital structure for nitrogen, each nitrogen, if you look at it at the periodic table, it has 5 valence electrons. So those 5 will be the ones engaged in bonding. So we're going to look at that when we draw our diagram. And as you know, it goes 2s2 and then 2p3. So those are what each box is. And we separate, as you can see, the lower one is just s orbitals, the higher one is just p orbitals. So how this works is you fill out the leftmost and rightmost because those represent your atomic orbitals. And then in the center is them coming together to make the molecular orbital. And back to the principle of conservation of energy, there should be the same number of electrons in your starting out atomic orbitals. So here we have 4 because there's 2s electrons and 2 from the other one. Those come together to make 4 molecular orbital electrons. So you fill up the sigma one and then the anti-sigma star. And you always fill bottom to up. So that goes for S and then sigma star because sigma is lowest energy and sigma star is highest. And then we go to P. So here we discussed earlier that P has 3 orbitals and they kind of show that through 2 sigma and 2 pi. You're starting with 3 electrons from the 2p orbital, and then you fill out each at the bottom and then each at the top. And you might be asking, I thought sigma is like lower in energy than pi. So why is it described as higher in energy right now and less stable? This is an exception. We love exceptions in organic chemistry. Some molecules do have this. Another one is O2, like oxygen's molecular orbital diagram. So later when I'm done speaking, I can find examples that are a more quote unquote normal one. But for now, let's just stick to these slides. So Aufbau's principle is filling up from the bottom to the top, and your bond order can determine stability. So it's your number of electrons in bonding molecules minus bonding molecules divided by 2. Basically, if you have more electrons in the bonding molecular orbitals, anything that's not starred, it means it's stable, and the bond is golden. If there's more electrons in your anti-bonding molecules, like for example, somehow if there were a molecule, the sigma ones weren't filled, but all of the sigma stars were, the pi ones weren't filled, but all the pi star ones are, that's a really unstable molecule and the bonding just wouldn't happen to begin with. So this diagram is basically just a way for us to conceptualize, is this bond stable enough to actually happen and for the 2 atoms to actually interact? So to summarize, just some differences between VB and MO theory. Sticking with valence first, well, I'll compare them, but each atom donates an electron for a bond versus in MO theory, bonds can move around instead of staying in their localized spot. So think resonance, lone pairs. And for VB, it explains hybridization through orbitals. So orbitals are a big part of it. But for MO, it doesn't really reference hybridization through orbitals themselves. For VB theory, the atomic orbital character is preserved, like there's no mixing, there's no molecular orbitals happening, but that's a huge part of molecular orbital theory. And one more, everything is localized in VB theory, but again, in MO theory, stuff is moving around, it's chaotic, there's resonance and there's lone pairs that jump. So those are the biggest differences. Sorry, Ashley, am I doing these?
No, I got that.
Right.
Thank you.
I can stop sharing my screen.
I'm gonna take over with my iPad.
All right. Thanks, everyone.
Thank you, Kristen. Okay, so let me just share my screen. Okay, so now we are on to conjugation and resonance. So to get kind of connect what we're talking about, Kristen just did a great job talking about all the orbitals that Dr. Tovar introduced you to and reviewed with you from Intro Chem 2. And so now we're moving on to the idea of resonance. And the idea of resonance is that molecules are able to stabilize themselves through resonance, which is the ability to delocalize or share electrons through multiple atoms. And this idea is allowed because when you have two carbons, let's say double bonded, and then you can have a whole entire conjugated system going on the other ends. These carbons have orbitals in which they can end up delocalizing their electrons and sending them to each other. And because they're able to spread it across the whole entire system, where I drew the two squiggles at the end, and then it could be an even longer conjugated system, and having that delocalization of the electrons throughout that system, it causes it to be more stable than just having it in one localized spot. And so a conjugated system, which is a word that I mentioned, is a system of atoms that have resonance. And in order to be a conjugated system, the molecule needs to have alternating single or pi electrons, which is often seen as double bonds or lone pairs. So one example of this can be if you have something very simply like this, where it's alternating between double bonds and single bonds. And then you can also have lone pairs in there. So if we had something at the end with a lone pair, where there would be a charge because of that lone pair presence, that can also be part of the conjugated system. And also keep in mind that with conjugated systems in a molecule, the whole molecule does not have to be conjugated. You can have parts of a molecule which don't belong to the conjugated system because they don't adhere to the necessary requirements. And then one other part that we wanted to highlight is the resonance hybrid. So the resonance hybrid is a way of representing what the molecule would actually look like in real life, as it's delocalizing electrons and sending them to each different carbon in the system. So just to look at this one that I drew above, if we wanted to draw the resonance hybrid of it, we could end up drawing just the regular single bonds of it. And then we would put a dotted underline underneath it or above it, just to represent that double bonds can be present there, which means that electrons are moving around. And then you can also have some of the partial charges as well. So because we had a lone pair there, we would also have partial negative charges here at the top, and then you would also have partial positives at the bottom, where there would be more of a positive charge since more of that negative charge is towards the top. And then we wouldn't actually have it there. And so it's just a way of showing like kind of the middle point of all that, all the different resonance systems, and kind of a very good summary of what's going on. So just to give a few more examples of resonance and make sure that you guys really understand what I'm talking about. Two examples that I wanted to go over, which I guess we kind of went over the first one with my example from above, is this one. So if we have something here where it had a lone pair and you have the negative charge, it's pretty easy to end up resonating this because one, you always start off looking at what is your conjugated system, what belongs. So here we see that the entire thing belongs in our conjugated system. Next, you're gonna look at where can you move the electrons. So from here, you can see that you have this charge and this electron pair that you can most likely end up moving. So when you're drawing a resonance structure, you're always going to want to end up moving your lone pair into the atom or bond that's most nearby. Like you can't end up skipping the bond or the carbon. That's a really big important process because if you end up skipping things, that doesn't actually represent what the resonance structure is. So here you would end up being able to move the electron pair into this bond, and then these electrons end up having to move because it would upset the hybridization of those carbons, and just to keep everything properly hybridized, you need to move them here. And that kind of goes back to the orbital theory as well, because this carbon has an orbital that the electrons can actually move into. So over here, just to draw an arrow back and forth, you end up getting the double bond there, you have a double bond here, and then now you have the lone pair here. And just to go a little quicker, you can end up moving this lone pair again, and then moving this double bond. And then you end up getting the double bond there, and then you get the lone pair there with this charge. And so to draw the resonance hybrid of it, it would look like that. And then if you wanted to put in charges, this is your positives on top, and then negatives on bottom. And then for the next problem that I wanted to go over is a little more difficult. What happens if you have a positive charge? So when you have the positive charge, you can't end up moving the electron pair just like you did before, because there's no actual electron pair to move. It wouldn't really make sense to do it like that. So just like we did before, we have to consider what can we move. We can end up moving actually your double bond here. So you can move this double bond to where that charge is and end up resonating here, and then you would have that, and then you would have your positive charge there. And then for the next part, you can also end up moving this double bond so that the positive is there. So it ends up having a very similar resonance structure. The big difference is where the partial charges are, because now the positives are on the bottom and the negatives are on the top. And then one other thing is always make sure that when you're doing resonance structures, make sure to avoid making a pentavalent carbon. A lot of times I think we see students accidentally making pentavalent carbons unknowingly. So always watch out that when you are moving your electron pairs around, that you're not accidentally forming a pentavalent. And then now we are on electronegativity and dipole moments. So this is just to kind of give a little bit of background, but electronegativity is just the measure of that atom's ability to pull electrons towards itself. I always kind of think about how greedy is that electron or that atom for electrons. And Kieran ended up putting this slide together and listed some of the important ones that always end up showing up with fluorine, oxygen, nitrogen, carbon, and hydrogen. And these are important to remember because oftentimes when you're looking at molecules, you can end up seeing if it has a dipole moment in it, and overall if the molecule has a dipole. So when you have electronegativity between two different atoms, you can find its difference. And then if it's in this range between 0.5 to 1.9, that can cause there to be a polar covalent bond, which is when there is a large electronegativity difference. And so you can see this down here where you have the oxygen with 3.5 and the hydrogen with 2.1, which has a very big difference and it has a molecular dipole. The same thing can be seen with the fluorine and the carbon, which have two very different electronegativities, and then you have that dipole forming. And just to keep in mind with the arrows, the bottom part forms a plus sign, so that's where the positive of the dipole is, and then the arrow is where the more negative part of the dipole is. These two last ones are often tricky because while they do have dipoles slightly between the atoms, the overall molecule does not have a dipole because of its structures balancing it out. So this carbon is tetrahedral, and it ends up having the fluorines with its dipole moments canceling each other out. So then overall, there's no molecular dipole. And the same thing is happening over here with the CO2, where you have one dipole going to the right and one dipole going to the left. So then they end up effectively canceling each other out and creating no molecular dipole. And for the next part, acids and bases. So just to go over, I know in one of our pilot sets, we went over the definitions, but just to recap, the Lewis definition focuses on acids and bases with respect to electrons, whereas the Bronsted-Lowry focuses on acids and bases with respect to hydrogens or your protons. And so a Lewis acid is when the electron, it is an electron pair acceptor, which is often termed the electrophile. And then your base is the electron pair donor, which is often termed the nucleophile. And so just to, I guess, give you guys an example of this, here, let me draw it out. So when you have these two compounds and they end up reacting together, I'll just have the arrow down here. It ends up forming these. And so what happens is you have the lone pair on your, oh wait, this was not supposed to have hydrogen. Sorry about that. You have your extra lone pair on your oxygen, which will then go and pluck off that hydrogen. And then this ends up being left without the hydrogen. So in terms of this, does anyone have any ideas on what would be the acid and what would be the base over here? You can put it in the chat or just shout it out. Yeah. So the left one is definitely the acid because it is the one that is like giving up that hydrogen and accepting that electron pair so that it ends up getting that negative charge. This ends up being your base. And just to kind of, I guess, go back to, I guess, introchem, this is your conjugate base, and this is your conjugate acid. And so to go over just some important acidity trends, the strength of the acid is determined by its conjugate stability. So in terms of acidity, the 5 major trends are charge, electron delocalization, electronegativity, and hybridization, size, and induction. So to just give, I guess, a little more description, when something has a stronger or higher charge on its atom, then it is more acidic. When it has more resonance or electron delocalization, then it's more acidic. And then for electronegativity, when it has more, it's more electronegative. And then for hybridization, when it has more S character, then it's more acidic. For size, when it's bigger, it's more acidic. And then for induction, that's when you have electronegative groups close to your other electronegative group. And it's able to end up pulling the electrons through the compound. That makes the more induction that you have, the more acidic it is. And so now we are on to part 2, which is your alkanes. So alkanes are your building blocks. So a lot of times they can also be shown as constitutional isomers. Just looking at a chemical formula, they can have different connectivity, which is the idea of a constitutional isomer. So looking at these two compounds here, they end up having the same chemical formula, where they have the same amount of carbons, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and then the same amount of chlorines, which are 2. The issue is that they're connected differently, and so they each have different names. So does anyone have any ideas on what the name of the left one is versus the right one? Mm-hmm. 2, 3, 4. So 2, 3 dichlorobenzene, and then 1, 4. And then I'm just gonna write that instead of writing out the whole thing. And so yeah, that's about it for all constitutional isomers. Just always be aware of, like, just given a chemical formula, they can be written or they can be bonded differently. Also in terms of your building blocks, they're different functional groups. So just to go over some of the big important ones, this was on one of the pilot sets just for naming and for getting you familiar with it. But your alkane is your single bond and it ends with A and E. Your double bond is an alkene, which ends with E and E. Your alkyne, which ends with a Y and E, is your triple bond. When you have one of your functional groups with an F or a chlorine or a bromide, let's say you had this with an F on, that is called an alkyl halide coming off. Other important ones that often look very similar are your ketones, but it has no hydrogen. Your aldehyde, which has a hydrogen. Your ester, which ends up having your oxygen there. And then a carboxylic acid, which is similar to the ester in that it has an oxygen there, but it has a hydrogen instead. And then 2 other ones that are very similar are your amide and amine. I always just remember that the amide has this special part, which makes it look a little bit kind of like a ketone or ester. Excuse me. And then you have your cyclohexane, which has no double bonds on it, and then you have your benzene, which has 3 double bonds. Okay, so now we're getting into what you guys kind of covered a little more recently in class with steric strain and looking at your different conformers and conformational analysis. So I think the official definition can get a little bit tricky to understand. I ended up just Googling like steric strain, and it said that it's the increase in potential energy of a molecule due to the repulsion between electrons and atoms that are not directly bonded to each other. I don't think it's really the best definition. And so this is my own. It's when you have the big bulky groups that are in the same space as each other and are repelling and pushing each other away. Because when you have a tight spot and then you have two big fat things, they're not going to go into it easily. Think about air when you're sitting next to two fat people. You're not going to fit in easily into that small little space. So in terms of steric strain, which one has more strain on it? The staggered conformer and the eclipsed conformer. Yeah, so it's your eclipse, and you can see it right here where you have these molecules which are almost directly overlapping when you're looking at it straight on, where they're very close to each other, and it's causing more steric hindrance. They don't like being that close, whereas the staggered one has them further away from each other. You don't have one where they're in a straight line with each other. Also, to just keep in mind with the eclipsed form ends up causing there to be more energy because of that repulsion, and as a result, it becomes less stable. All right. So now to get on to a little bit more difficult of an idea is Newman projections. So Newman projections are a way to easily visualize rotation around a single bond. And so it is using that idea of your conformer from above, and you're trying to rotate on this bond right here. So you end up rotating on this bond. And so one way that my TA and pilot leader ended up teaching me on it, shout out Patrick, he ended up always drawing this eyeball thing, which was a little bit creepy, but it got the point across. Whereas imagine that your eye is looking down that line. You're gonna have this front carbon, and then you're gonna have this back carbon. So this front carbon corresponds to that dot there, and it corresponds to these lines. Your back carbon corresponds to this bigger circle and these outer lines. So when you're trying to convert from just your regular drawing of a molecule into the Newman projection, I always ended up drawing that eyeball to kind of help situate me. And then you can say, okay, on my first carbon, I have an Me, I have another Me, and then I also have this implied hydrogen. So then I'm going to write Me, and hydrogen. And then for the next part, you're going to look at your back carbon. So you're going to see, oh, I have an Me here, and then you have one hydrogen here, and then you have another hydrogen there. So you're going to end up writing it again, Me, hydrogen, and hydrogen. And so that's how you end up converting it just into one of the conformers. It also, just keep in mind, doesn't really matter. So you can end up putting this Me here or here, as long as you're being consistent with how you're drawing it around the molecule. And so when you also get into the conformational analysis where you're rotating around, that's where you just have to be a little more consistent on that part. But you can draw it anyway. And then, so to move on to look at conformational analysis, so when you're actually rotating the carbons, I always used to draw it again where you see your Me and H and Me, your front ones, and you just leave them in the front as is. So when you're rotating that back carbon, the front just stays the same. So I always had it so that it was very consistent and easy for me to draw these. So you can do ME here, ME here, and H here. And then you would also have ME, ME, and H. ME, ME, and H. Now, when you move on to the conformation analysis part where you're rotating the back carbon, so I always would draw it like this, where I see that the hydrogen is ending up moving over. So then this eclipsed form will just show that it's starting to be, that it's behind the ME. So you still have the hydrogen here. This hydrogen corresponds to that hydrogen. This hydrogen is there, and the ME is there. Once it finally rotates 120 degrees, that's where you'll see that it flips parts of the molecule. So this hydrogen will now go over here. So you'll have hydrogen, hydrogen, and ME. And then we'll do the same thing again, where you get the ME, hydrogen, and hydrogen. And then you can rotate it so that the ME finally comes to this side. So you get ME, hydrogen, and hydrogen. So all these different forms are ways that the molecule can exist because you're rotating around this double bond, and single bonds are able to be rotated around. The only difference is that some of these different conformations are more or require more energy because there's more sterics involved. So when you see something like this where it has a ton of MEs right next to each other, they're not going to like that as much as when they're a little more separated. So this would have a lot higher of energy. So let's actually look into this. So just to talk about the interactions that I was talking about, these are estimates that I used when I was in the class of what these interactions would cost. So when you have hydrogen eclipsed on top of another hydrogen, it's a 4.0. Hydrogen eclipsed on top of a methyl is 6. And then ME or methyl eclipsed on top of methyl is 11. And then gauche, so when it's staggered between two methyl groups, is 3.8. So to look at the example of trying to find the energy of the three conformers, you end up I always like to color code them, but since you might not have color coding on your exam, maybe circling, but just for the sake of since we are here and we are able to. So these are your first three, which are your eclipsed ones. So it's only going to correspond to this. When it's eclipsed, it can only be when it's in that form, whereas this gauche or gauche, I think is what my pilot students were telling me Tovar pronounces it as. It's only going to be in your staggered form, which is here and here. So you see that you have an MEH, MEH, and MEH eclipse. So that will be, MEH eclipse. So that will be your 3 times 6, which is 18. And then for your next part, you see that there's ME, ME, and then it's in your staggered form, so that it's just 3.8. And then just to keep units, kilojoules per mole, kilojoules per mole. For the other one, you end up seeing that you have an ME, ME gauche as well. So then you get 3.8 kilojoules per mole as well. So now that you've calculated all three of those, you can end up looking at this on a graph and finding out the barrier to rotation. So just to rewrite them down, you have 3.8 kilojoules per mole. You have 3.8 kilojoules per mole. And then you have 18 kilojoules per mole. And so this is when you're at 0 degrees, nothing has been rotated. This is when you're halfway and you're at 60. And then this is when you're at 120 degrees. So you have done the full rotation. So when you're trying to draw an energy diagram for this, you can end up drawing it like this. just make it easy with 0 degrees, 60 degrees, and 120. And then this is your energy on the side. So you can have 3.8 and then 18, not the most to scale, but it's okay. And so then you say you have 3.8 there, you have your 18 here, and then you have your 3.8 here. So just connect the dots. It's a little shaky, but it's okay. And then that is how you get your energy diagram for just the rotation there. Also, just I saw that someone's message in the chat was why not have the 0 on the axis. That was just like a personal choice of like graphing it out. You could easily put it on the axis. And then in terms of finding your barrier of rotation, you end up just doing your eclipsed form minus the initial staggered form, because you end up looking at the energy difference between this and this, which is your eclipsed and your initial. And so it always reminded me of the idea of kind of like activation energy that you learned in intro chem, of how much energy do you need to kind of get over that hump. And so this is the amount of energy that requires you to get to the most energy like demanding point. And then once you get to that point, it's smooth sailing back to the other staggered conformation. And so just to actually calculate it, you end up doing your eclipse, which is your 18, minus your staggered, which is the 3.8, which is 14.2. Yes, 14.2 kilojoules per mole. All right. So that is about it, I think, for your different conformers and rotating. It's really not too bad. Just always keep the front the same, and then you rotate the back, and then you can end up calculating your things based off of the different energy values that Dr. Topper will give you. Now to move on, so you have cyclic molecules and chairs. In terms of stability, your most stable molecule will be your 6-membered ring. 5-membered rings are also pretty stable, and though they will definitely be showing up in Orgo for you guys. The only thing is that rings that are smaller than 5 and bigger than 6 most likely won't be showing up nearly as much, because they become progressively more and more unstable due to ring strain. So you won't be seeing a ring that's like a triangle or a square or a heptagon. I think it's heptagon for 6 or 7. And then like an octagon, you wouldn't see that either. So your 6-membered rings are your most stable. And that's when you can adopt a conformation known as a chair. And so they end up doing that because it looks like a kind of like one of those like tanning chairs at the beach where you can have a person and they're chilling and they're just like, yay, I'm relaxing. I don't think it's the cutest thing, but it's okay. And so you end up getting this hexagon. And just to prove it to you guys, if you count up the number of corners, you get 1, 2, 3, 4, 5, 6. It ends up being the same. And the only reason why it can end up looking like a chair is because they're taking advantage of the fact that single bonds are able to rotate. So they're rotating this kind of nice looking hexagon into something that looks more like that chair. So now let's get into the different parts of the chair. So sorry, let me just get some water. So when you get into the different parts of the chair, there's something called axial. And there's something called equatorial. Axial is when it is straight up and down off of the chair conformer. Equatorial is when it's kind of going off to the sides. And so I always remembered what way the different ones were going off of my carbons. Sorry, my throat is very dry. I remembered what way they were going off of my carbons by thinking of kind of like the zigzag that you end up forming when you make long chains. So you always end up wanting to go up, down, up, down, up, down. So you see this one is going down, this one's going up. So then you're gonna want your equatorial going down. So then you have it right here with it going down. Actually, I'm gonna make it going right. For your next one, so that means off your carbon, the axial, because you'll have something that's axial and something that's equatorial, up or down on both carbons. That means for your axial, it will be going up. For the next one, since you just had something that was equatorial going down, you're going to have something going equatorial going up because it always flips. And then you end up having something going axially down. And so this pattern ends up continuing along so that your axial ends up going up here, and then it also goes up here. Or your axial, and then your equatorial goes down, and your equatorial goes down. And then your equatorial here will go up, this one will go up, and then you'll have axials going down. And then just to color code. So yes, that should be it. And then moving on to an example of trying to change your substituted molecule into a chair. So when you're drawing the chair, it's always helpful to draw it with your two parallel lines next to each other. And then you end up drawing these lines that are parallel and then drawing up and drawing up. And then I always end up having to do a little bit of shifting around to just see like that one doesn't look so nice. To make it look a little bit better. Honestly, my chairs are not that great. They're kind of ugly, I'm sorry. But it kind of gets the point across. So when you're doing a problem like this and you're trying to turn your molecule into a chair, you'll always start by numbering. So always number your carbons because it will make sure that you don't accidentally make any silly mistakes. So here, 1, 2, 3, 4, 5, and 6, and I'm just choosing randomly for what makes me feel comfortable. It doesn't matter where you start, whether it's on this molecule one here or anywhere else, as long as you're being consistent when you draw where these substituted parts are. So just keep in mind that with your wedge, it goes up, and with your dash, it goes down. And so now here we have number 1, and we see that it's going up. And we just drew a chair conformer before, and we figured out what goes up and what goes down. So to work on this problem, you can see that we need something that goes up. It doesn't really make sense because your equatorial will be going down. So now we know that it will probably be axial. So it will be axial and going up. For the next one, we're going to look at 2. So right here. Does anyone have any ideas, since it'll be going down, on whether it be axial or equatorial? It'll be down. And then someone's asking, why is it axial? So you wouldn't have, so when you have on your carbon, you always have something axial, something equatorial, and then either one of them will be going up or down. So before, we were trying to figure out what was going up and what was going down on our molecule. From here, I always do the zigzag idea for figuring out what's equatorial. So with equatorial, it will be going up. So then your axial is forced to end up going down. So that is why for number 2, axial will end up going down. And this also matches because you need your wedge going down. So that's what you need, and then you won't have your equatorial there. Also, just keep in mind that when you have something going axial up, the carbon next to it will have an axial going down. And then for number 4, does anyone have any ideas on, so since it has to go up, whether it's axial or equatorial? Yes, so it is equatorial, so it's going up. So just, I think. So you end up figuring out this chair conformer. So a lot of you must be saying, well, then why can't you draw it in another chair conformer the other way? Like this, where it goes. Okay, let me redraw that chair. Where it goes. It can be drawn in either conformation. So that idea is a ring flip. So you can start with one of the chair conformers and number your carbons, and then you can end up flipping everything so that it matches the other chair conformer. So just because I don't want to draw chairs again, I'm just going to copy this all down. Okay, so if we're trying to draw this ring flip to the bottom ring, you just start with your conformer. You have the carbons already numbered here. You draw the mirror image of the backbone, which is right below it, and then you shift the numbers by 1. So when you shift the numbers, you go 1. All right. And so then when you, did I shift them? Okay. When you shift your numbers, it ends up flipping just the axial and equatorial. So for 1, we had something that was going up, but now it's going to become, instead of axial, is going to be equatorial. For number 2, we had something that was going down, which it will still stay down, but then instead of axial, it's now become equatorial as well. For number 3, or there's nothing for 3, number 4, we had something that was going up, so it'll still stay up, but then you have something, instead of axial, it's now becoming, or instead of equatorial, it is now becoming axial. Oh, wait, it was going up. All right. So that would be your ring flip. And then just like our different rotations around conformers, different chair conformations have different energy differences. So these were the common values that I used when I was in Orgo. So they were both actually the same with 3.8 and 3.8. So you had the gauche and the ME, and then you had the 1,3 diaxial HME. So now let's find the energy difference between these two conformations. So in terms of finding a 1,3 diaxial HME, you're going to count from that methyl group and then go 1, 2, 3. So you do 1, 2, 3. This will also have a hydrogen that's going up because it's also axial. And then this also has a hydrogen. So these actually have the 1,3 diaxial HME interaction. What's also tricky is that they can also be going down. So just to show it going down, on 2, you can have the hydrogen and the hydrogen, and you can have the 1,3 diaxial interaction, so that you end up having 4 1,3 diaxial interactions, and then it ends up being a cost of 3. And then you get a value of I think 15.2. And then for your other conformer, you're able to do, or conformation, you're able to do that same idea with your 1,3 diaxial. So 1, 2, 3, the hydrogen is here. You also have another hydrogen there. So you get the 1,3 diaxial, and then the one thing that can be tricky is finding the gauche Me-Me interaction, because with a gauche Me interaction, as long as both of the methyl groups are either going up or down or are equatorial and are next to each other, that constitutes a gauche Me interaction. So because these are both equatorial and are right next to each other, that causes it to be a gauche interaction. If they were both going down, regardless of equatorial or axial, they're also gauche. Same idea if it's going up. So then on this conformation, you end up having the gauche interaction, and then you have the two 1,3 diaxial, so it's 3 times 3.8, which is 11.4 kilojoules per mole. And then your difference in energy is just then 11.4 minus 15.2, which is negative 3.8 kilojoules per mole. And then I think that should be about it for your tumor conformations, I believe, yes. So I just always remember to count your carbons, and when you flip it, you have to shift them over. And then I always remember the zigzag pattern for trying to figure out if something's axial or equatorial and going up or down. Okay. So Juliana, I think, are you doing nomenclature?
Yeah, hold on, give me a second.
Yeah,
Do you want me to share my screen, or do you want to just, okay. Okay, can everyone see that?
We're able to see.
All right. Okay, so we're just going to go through some basic nomenclature, and this is based off of what Dr. Tovar talked about in lecture, because there's a lot of complicated stuff that you guys are not expected to know. And so basically we can start with alkanes. An alkane is basically a molecule that only has carbons and hydrogens, so it's a hydrocarbon, and it's joined by single bonds because it's an alkane with an A. So it has a chemical formula of CnH2n+2. And so the first step is to find the number of carbons in the longest possible carbon backbone. So be sure to look at like any possible branches, because that could be the longest carbon chain. And then the other things would be the substituents. And so once you know how many that is, that becomes the last part of the name. And so basically, if it's 1 carbon long, that's meth, prefix, 2 is eth, 3 is prop. And so one little mnemonic to remember that by is, I use mom eats peanut butter. So like MEPB for methyl propyl butyl, basically. Another one that I was taught by my former TA was monkeys eat purple bananas, whichever one you want. And so once you have that, you want to actually number it. So usually there's like 2 ways to number it. And you want to get the lowest numbers with the substituents on like the smallest numbers, basically. And so here highlighted in blue, you can see like a general formula to name your hydrocarbon. And so if there are multiple identical substituents, then you use di for 2, tri for 3, tetra for 4. I know there was an example on the constitutional isomers slide where some people forgot to put the di, but that's just like a little mistake. So be sure to double check when you're naming your compounds. And so if there's a conflict with numbering your carbon chain, that carbon backbone, always use the smallest possible numbers. And so if we look at the image on the bottom, the first one, we want to say 2-methylpentane, not 4-methylpentane, because 2 is smaller than 4. And so that same logic applies to the second one and the third one. And then if we look at the last one, the one on the very right, we have 2 substituents coming out, one ethyl and one methyl. And so we want to name this 5-ethyl-3-methyl octane because we have 8 carbons in the backbone. One ethyl group, the ethyl group is the one on the more right side. The methyl group is the one more on the left side. And the reason why we chose 5 and 3 is because the smallest number 3 is less than 4. And also, I think Dr. Tovar said this in class, if you add 5 and 3, that's less than 4 plus 6. So that's why we number it like that. And the ethyl goes first, even though it's the bigger number, because E comes before M for methyl. And one thing to note is that the prefix for if you have multiple identical substituents, the di, the tri, the tetra, that does not count into the alphabetical order. Okay, and then continuing on, if you have a cyclic structure, pretty much the ring will be the parent hydrocarbon. I don't really think there will be any tricky examples where that isn't. And so once again, if there are 2 substituents, list them in alphabetical order. The first one is carbon number 1, so very similar to the straight chain carbons. If you have more than 2 substituents, then you list in alphabetical order, then give the carbon number 1 to the substituent that gives you the lowest possible number. And this is getting a little bit complicated. I honestly doubt that he's going to straight up test you guys on this, but essentially, first step, find the longest carbon parent chain. 2, number the chains so you get the smallest possible numbers. 3, list the substituents alphabetically, not counting the prefixes, di, tri, tetra. And I just want to say again that nomenclature is not going to be a huge focus. Don't get too hung up on the small details. On the exam, you are pretty much not going to see a question where you get the IUPAC name and then you need to draw the structure and then you can do the problem. He's just going to give you the drawn structure. So yeah. Any questions? I think this is the last slide.
Alrighty,
Oh,
so
sorry, can I just say one thing? Yeah, there is a priority chart for functional groups too, but I'm pretty sure he didn't even show that in lecture, so yeah.
So just to answer some of the few things in class or in the chat, in terms of extra practice problems, there will be one more problem set for pilot that you guys do this week that you guys will have extra practice on. So yes, there will be more patches coming, and potentially you will also have some extra time during those sessions to just work on like a Q&A sort of thing with your pilot leader if they wanted to go over previous problems or go more in depth on why certain things were done on different problem sets. To talk about the other stuff for StereoChem, I don't believe StereoChem will be on your exam. Please don't quote me on it. I have not seen it, so I have nothing to like go based off of except for an email that I had with Tovar. And he said that it would mostly be focused on the first 3 chapters. I don't think in lecture you guys have covered too much StereoChem really at all. He said everything would be fair game up until Friday's lecture. Like Friday's lecture included is all fair game. I think your Monday and Wednesday lecture won't be included. Do we need to know about ISO? Oh, I think someone answered that. I think Maggie did. And then yes, just wondering, will we be tested on cis trans for the exam? Truthfully, I don't think.
No.
Yeah, I don't think that there was really much covered on cis and trans for your exam, so I don't think it will be covered, but if you want to know more specifics, maybe ask him. And then, when referring to a 3-carbon molecule, the common name associates with ISO with the primary 4-carbon. If someone is a little more.
Victor, I'm not sure if I'm interpreting your question right, but I think it's probably to distinguish between the 2 possible carbons, because when you have a 3-carbon molecule, the only possible iso position is the one in the middle. I'm not sure if I'm answering your question right. Eureka, sorry if I didn't pronounce that right. That just kind of depends on the reaction itself. Yeah, it changes between reactions depending on whether it's an acid base, for example, or a nucleophile attacking. So it really depends. There's no general rule for it. I wouldn't memorize pKa values, but I would kind of know a general ranking of how acidic something is. Like carboxylic acid are more acidic than alkanes, for example. I think Dr. Tovar will want you to be able to determine the direction of equilibrium reactions more through reasoning about which conjugate base is more stable and which one is a better acid, as opposed to just memorizing pKa values.
Okay, to go to Krista's question, I'll pull it up just for saving space on my laptop, just since this is Q&A. I think if it's okay, I'm just gonna stop recording since we finished the lecture portion. So just to say a wrap up to everyone, good luck on your exam. If you do have questions, please feel free to ask your pilot leaders questions during your session, and also do please go visit your TAs and Dr. Tovar, and good luck on it. I'm sure you guys will all do well. I know it's Saturday nights and you guys are all working hard.
Before you end the recording, I just wanted to address a question that was kind of confusingly worded on one of our pilot sets. Is it okay if I share my screen?
Yeah, go for it.
Okay, awesome. So, sorry, my computer is lagging. So this was the acid-base question that asked for the HOMO-LUMO of the long conjugated system. Oh, not this one. Okay, so in this question, for part B, it was kind of confusing when we say identify the HOMO and LUMO of the reaction. So HOMO and LUMO is a more general term that refers to the entire molecule. So in this case, the LUMO of the molecule is the pi star antibonding orbital, but the orbitals that are involved in the reaction themselves that we drew out in the acid base reaction is the sigma star antibonding orbital. So a better way to word this question would have been like identify the two orbitals involved in the reaction, because HOMO and LUMO is a more general term that refers to the whole molecule. Cool. Yeah, that was just what I wanted to say.
I